All right, section 7.12, 7.12. I don't know why I said 7.12. Behavior of real gases. Up until now, largely we've been talking about ideal gases rather than real gases. So what we're going to do is talk now about real gases. So real gases, what makes them different is ideal gas behavior is based on two assumptions. First of all, the volume of a gas particle is negligible, and no interactions, attractive or repulsive, take place between gas particles. At high pressures and low temperatures, these assumptions are not always valid. So high pressures and low temperatures, things get a little bit different. So those are the two kind of areas to think about. The van der Waals equation allows you to make more accurate predictions regarding the pressure of real gases. So what this shows us here is real gas particles have finite volumes. Very high pressures force the gas into very, very small volumes. So what we see here is a relationship between, or a ratio of pressure and volume divided by R value and our temperature versus pressure. And as you see that temperature change, so practice problems to kind of look at with this is this sort of thought exercise. If you have 1 mole of each of gaseous F2, Cl2, and Br2 at the same temperature and very high pressure, which do you expect to have the largest measured volume? Well, atomic radius increases as you move down a periodic table group. So Br has the largest radius of the 3 halogens, making Br2 the largest molecule. So largest molecule. At very high pressures, the volume of the particles may not be negligible. So very high pressures, that volume is not negligible. Bromine, having the largest particles, is expected to have the largest deviation from the ideal behavior, and thus the largest volume. So our question was, when you're comparing these 3, well, what's going to have the largest measured volume? Well, when we compare these 3, what we needed to do is we needed to think about what is the size of those individual atoms, and therefore what is the size of that overall molecule. And we figured out that Br2, based on the trend in the periodic table, Br2 is the largest of those 3 molecules. Therefore, it's going to have the largest volume and the largest deviation from ideal behavior. Now, interactions between particles. Attractions form between real gas particles, but these intermolecular forces tend to be weak because of the distance between gas particles and their speed. At higher temperatures, the particles move too fast for these attractions to be significant. At lower temperatures, the kinetic energy is lower and the collisions are less energetic, allowing attractions to have an impact on the pressure. Now, the van der Waals equation, which we talked about a little while ago. The van der Waals equation is the modification of the ideal gas law, introducing factors that are specific to each gas. If you remember, in the ideal gas equation or in the ideal gas law, we never talk about what is the identity of a particular gas. Well, we're going to take that into consideration whenever we're doing this. So the first factor involves volume. Volume is increased by a small factor related to the number of gas particles, N, and a constant specific to each gas, B. Okay, so V of a real gas, the volume of a real gas, is equal to nRT divided by pressure plus N times B. Okay, so these variables, the number of particles and a constant specific to each gas. So ultimately that gives us the volume minus NB is equal to nRT divided by P. So pressure is decreased by a small factor related to the number of molecules, the volume, and a constant A specific to each gas. Pressure of real gas is equal to nRT divided by V minus A, which is a constant specific to each gas, times N over V squared. Now, what this tells us, or what we need to do, is take these two things, these two components of this, and basically produce the van der Waals equation. So the pressure of a real gas and the volume of a real gas ultimately extends to this equation right here. P plus A times N over V squared times V minus NB is equal to nRT. So here are a number of different van der Waals constants, and this is the sort of thing that would be provided to you in a question, whether it's on your homework or a quiz or anything else like that. These are all the van der Waals constants, A and B, for a specific gas, whether it's CH4, CO2, Cl2, NH3, and so on. So these are all factors that you would have to consider when you're solving that sort of problem. Now, calculate the pressure of 1 mole of argon gas at 7.50 liters. So N is equal to 1.00 moles AR. V is equal to 7.50 liters. Temperature is equal to 273 Kelvin. Using the ideal gas equation, the van der Waals equation, and explain any difference between these results. Okay, so I'm going to do part A. A is solving, well, what's the pressure given the ideal gas equation? So PV equals nRT. And then I'm going to contrast this with the solving with our van der Waals equation, which is B, and I'm going to do that down here. Okay, so PV equals nRT. I'm solving for pressure, so I want to go ahead and say P is equal to nRT over V. So N is 1, R is 0.08206 times my temperature, which is 273, and I'm going to divide that by my volume, which is 7.5. My pressure, therefore, is equal to 2.99 ATM. Okay, pretty easy. Now, the van der Waals equation, I need to be able to use the values that I got, or that I have, or my van der Waals constants, for each of my, for that A and B. Okay, so the equation is, or the van der Waals equation is P plus A times N over V squared, V minus NB equals nRT. Now what I want to do is I want to isolate P, or pressure. So the way that I'm going to do that is I'm going to rearrange this so that I get P is equal to nRT divided by V minus NB minus A N over V squared. Okay, so I divided each side by V minus NB, and then I subtracted this A. So I divided by this, and then I subtracted this, and that's how I got this equation right here. Okay, now what I need my constants. So for argon gas, for AR, my A value is equal to 1.336. Okay, my B value is equal to 0.0320. Okay, do I know everything else? I do. So I'm going to swing this up here, and I'm going to say P is equal to, I'm just going to start plugging values in. So N is 1. Multiply that by 0.08206. Multiply that by my temperature, which is 273. I'm going to draw a line to really separate this. 273, divide that by my volume, which is 7.50 minus NB, which N is 1, and B is 0.0320. minus A, which is 1.336 times N, which is 1, over my volume, which was 7.50, and I'm going to square that. So I'll say 1 times 0.08206 times 273 2.9998 minus, and then we've got 1.336 times 1 divided by 7.5, and then I'm going to square that, which I got to find the square function on my calculator. Is that right? That is right. That's 0.017777. I'm just going to multiply that by 1.336. So I've got 2.998 minus 0.02375. 2.998 minus 0.023751 equals 2.97 atmospheres. Okay, so we see that our gas does behave a little bit differently. It has a different pressure is exerted, and the pressure is slightly lower whenever we utilize that van der Waals equation, because we're taking into consideration, well, what's the identity of our gas? And we see that played out right there. All right, well, I hope this is helpful, and that wraps up chapter number 7. We'll be on to chapter number 8, which, if I remember correctly, chapter number 8 is all about the quantum model of the atom. So we'll get to that. We'll be good. All right, have a good one, everyone.